All right, welcome back, everyone. We are continuing through Chapter 2, and today we will be talking about atoms. Remember from early on in Chapter 1, atoms were the smallest thing that biologists typically deal with. There are some smaller things than atoms that we will be talking about today, but as a general rule, we always say atoms are the smallest unit that we deal with here in biology. Now, in our next lecture, we're going to build on what we learned today. Today's going to be a very brief lecture where we're just going to talk about atoms, what they are, their structure. And in our next lecture, we're going to start to talk about how those atoms interact with each other. So it's very important to make sure you understand everything that we talk about today. And if anything that we talk about today doesn't make complete sense, make sure you ask questions to get that cleared up. Otherwise, our next lecture isn't going to make any sense either, and you'll get bogged down before we even get a chance to get rolling. So, let's begin, like we always do, with our not really attendance questions. First, water, which is H2O, belongs to which level of structural organization? And next, ATP is the energy molecule most used by our body. It has a lot of energy stored in bonds between three phosphate molecules attached to an adenosine molecule. What type of energy is ATP? So go ahead and pause the video, try to answer those, and then undo the pause and see if you got those answers correct. Okay, so hopefully you paused the video. Hopefully you tried to answer those questions. Let's see what we've got here. Water, H2O, belongs to which level of structural organization? Let's go back to our levels of structural organization that we've been looking at. And water, H2O, is at the chemical level of structural organization. Specifically, it's a molecule. So it is some atoms joined together. But it's at the chemical level. And next, ATP is an energy molecule most used by our body, has a lot of energy stored in bonds between three phosphate molecules attached to an adenosine molecule. What type of energy is ATP? Now remember, we said that it's a little bit nitpicky, it seems like, but here the key word is type of energy. That's very important here. So there are types of energy and there are forms of energy. Type was either kinetic or potential. And forms were things like the electrical energy or thermal energy or electromagnetic, which is thermal is a type of electromagnetic. So anything like that is a form of energy. We are talking about type. Well, the key word is energy stored in bonds. Stored energy, remember, was potential energy. If I instead asked what form of energy is ATP, it would be chemical energy. Remember, chemical energy was energy stored in chemical bonds or released from chemical bonds. All right, let's dive in and talk about atoms. Atoms are the smallest unit of an element. And they are the smallest unit of an element with the same properties of that element. So we talked about elements in our previous lecture. And we said elements each have unique chemical and physical properties. Atoms are the smallest unit of that element that have the same unique chemical and physical properties. Now, let's say you have a little piece of gold, and if you cut that piece of gold in half, you still have pieces of gold. And if you cut one of those in half, you have pieces of gold, and you could keep cutting it in half, smaller and smaller and smaller, but it's going to still be gold. It's just going to be smaller pieces of gold. But if you had the right machinery, you could cut that gold down to the point that it is just a bunch of gold atoms. You could not cut that any smaller and still say that it is gold. A single gold atom is the smallest unit of gold that there is that is still gold. Same thing with hydrogen or oxygen or sodium or anything like that. Once you get down to the single atom of an element, that is the smallest unit of that element. Now, there are things, like we said, smaller than that. But if you were to go smaller than the atom, it is no longer the same element. It's no longer an element at all. So let's talk about the structure of an atom, atomic structure. And if you take a chemistry class, you will learn that there are actually several different ways that we draw atoms. And here we see two ways to draw those atoms. Over on the left is what we will be using in this class, or a variation of it. This is the planetary model of the atom. So what does that mean? Atoms have three parts. They have protons, neutrons, and electrons. Another way to look at it is atoms have two regions. They have the area in the middle called the nucleus of the atom. Now, we're going to use the word nucleus a lot this semester, and each time we use it, it's going to be used a different way. So don't let that confuse you. Right now, when we talk about the nucleus, we are talking about the nucleus of an atom, and it's right in the middle. And then there's another area called orbitals or shells. And those are rings that go around the nucleus. Some elements have atoms that only have one orbital or shell. Some other atoms have multiple orbitals or shells. Now, what is the difference between the nucleus and the orbital or the shell? The nucleus is where we find the protons and the neutrons. The orbitals, shells, are where we find the electrons. So what are protons, neutrons, and electrons? These are those things that I said are smaller than an atom. So atoms are made of protons, neutrons, and electrons. They are different from each other, but every proton is the same. Every proton anywhere in existence is the same. Every neutron anywhere in existence is the same, and every electron anywhere in existence is the same. If we look at protons, every proton is the same size, the same mass, and it has a positive charge. Sometimes we write it as a P with a little bitty plus next to it. Sometimes we write just a plus, or sometimes we write H with a little bitty plus next to it. Those all mean the same thing. We'll see why a little later. Neutrons have no charge at all. They are neutral, which is why they're called neutrons. Protons and neutrons together are found in the nucleus of the atom. Electrons, they're much smaller than protons or neutrons. We won't worry about that in chemistry class. That's a big deal. But electrons each have a negative charge. They are found in the orbitals, the shells. So we've said protons have positive charge, neutrons have no charge, electrons have a negative charge. Protons and neutrons are found in the nucleus. Electrons are found in the orbitals. Now, what do we know now about the charge of the nucleus? Well, the nucleus has a positive charge, because if that's where the protons with positive charge is found and neutrons with no charge at all, we have a bunch of positive and no charges. So the nucleus has a positive charge. If we look at the orbitals, the shells, what type of charge do they have? They have a negative charge because the only thing found there are electrons, and electrons have negative charge. Now, in its natural state, every atom has the same number of protons and electrons. I'll say that again. In its natural state, every atom has the same number of protons and electrons. Think about that for a moment, and now tell me, what charge does an atom in its natural state have? An atom in its natural state has no charge. That's because the nucleus has a positive charge from the number of protons. The orbitals, the shells, have a negative charge from the number of electrons. And if the number of protons and electrons are equal, they balance out. The same number of positive charges and negative charges. The number of neutrons doesn't matter because it has no charge. Now over here we have another way of drawing atoms. Here we have the nucleus in the middle, and we have something called an electron cloud. And the electron cloud is where the electrons are found. But they're constantly moving around very rapidly. They're very small. So instead of drawing individual electrons, it's just kind of this hazy region. So we will not use this type of drawing. We won't use any of the other types of drawings that we don't see here, just because it gets a little bit confusing. You'll see them in chemistry at some point, if you take chemistry. And instead, we are going to use a variation of the planetary model. We will start drawing a few atoms as examples in just a few minutes. But for right now, if this slide did not make sense and everything that I was saying, if it didn't make sense, rewatch this part, because we're about to build on it just a little bit. And then in our next lecture, we will build on it quite a bit. So make sure that slide makes sense before moving on to here. What we see here is the periodic table. Most students have seen this at some point. Some students might not have. You do not need to memorize this. You need to know how to read it if it's in front of you. I will provide it on any exam that you need it for. So we need to know first, how do we read this? What does it mean? Well, this is a list of all known elements. The letters that we see there are called chemical symbols. Each element has a chemical symbol. Beginning up here in the top left, we have H, that is hydrogen. Over here we have He, which is helium. Then we go lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so on and so on. You do not need to know the names of them. Many of them you will get used to knowing their names because, like I said previously, we're going to talk about some of these a whole lot. So you'll just kind of pick them up from repetition. But I am not going to just ask you, what is SN or something like that. And I also will not ask you, what is the element that has 17 electrons or anything like that. Don't worry about that. I am more concerned with you knowing how to read this chart, which we're going to go over, and then the things that we talk about in the next lecture. So let's see how to read this chart. Up here, we have an H, which we said is hydrogen. At the top of the box is a number 1. At the bottom of the box is 1.0079. First thing we will say is when we have a number with a decimal and several numbers after it, we are going to round it to the nearest whole number. So what that means is in the H box, at the top is the number 1 and at the bottom is the number 1. Over here at He, helium, at the top is the number 2, at the bottom is the number 4. Lithium, Li, at the top is the number 3, at the bottom is the number 7. So it doesn't matter if we round up or down, we're just going to round to the nearest whole number. Now, what do all those things mean? We said the letter in the middle is the atomic symbol. That tells us the name or the abbreviation of the element that we're looking at. The atomic symbol is the abbreviation or the symbol for the element that we are looking at. In some cases, it makes perfect sense. H is the first letter of hydrogen. He are the first letters of helium. So sometimes it's very straightforward like that. Other times we have something like Na, which is the chemical symbol for sodium. There's not an N or an A anywhere in sodium. Well, what we end up having are some chemical symbols that come from Greek or Latin. And it's just accepted that Na is sodium. Now, what about the rest of it? At the top of each box, there is a number. That number is called the atomic number. And that's part of how this chart is arranged. The atomic number, 1, and then 2, and then we go down to the next row, 3, 4, 5, 6, all the way down. The atomic number is unique, and it is the definition of that element. So what do we mean by that? Well, first, the atomic number is the number of protons that that element has. The atomic number is the number of protons that that element has, and it is the definition of that element. We're going to put those two things together. The atomic number is the number of protons. In the case of hydrogen, it has 1 proton. In the case of helium, it has 2 protons. In the case of lithium, it has 3 protons, on and on and on. And if we say that that is the definition of the element, what we're really saying is the definition of hydrogen is an atom with only one proton. The definition of helium is an atom with only 2 protons. The definition of lithium is an atom with only 3 protons. If we have an atom and it has 1 proton, we know without a doubt that it is hydrogen. If we have an atom that has 19 protons, we know without a doubt that it is potassium. The number of protons defines the element, and it is constant. If we have an element and we know the number of protons, we know what element it is. And if somehow we used a device to remove a proton, it becomes a different element. As a general rule, we say that the number of protons does not change. In reality, it does, but that's a chemistry and a physics concept. For our purposes, as a general rule, the number of protons does not change. And the number of protons is both the atomic number and the definition of the element. At the bottom box, the bottom number in that box is the mass number, or the atomic mass. In the case of hydrogen, it's 1. In the case of helium, it's 4. In the case of aluminum, it's 27. So the number at the bottom of the box is the mass number, or the atomic mass. Those two terms are interchangeable. I'll call it the atomic mass more often. So the atomic mass is the number of protons plus the number of neutrons. The atomic mass is the number of protons plus the number of neutrons. So really, if we go back, the atomic mass is the number of things in the nucleus. So in the case of hydrogen, we see that it is 1. If we know that 1 is the number of protons plus the number of neutrons, and we know that hydrogen has 1 proton, how many neutrons does hydrogen have? 1 plus what equals 1? 0. Hydrogen has 0 neutrons. Hydrogen has 0 neutrons. It has 1 proton, 0 neutrons. Put that aside for a moment. We're going to come back to it. Helium. Helium has 2 protons and atomic mass 4. So how many neutrons does helium have? 2 plus what equals 4? 2. So if we go back, here is our drawing of helium. We saw the protons are the red things. There's 2. Neutrons are the yellow things. There's 2. There's 4 things in the nucleus, and that's our atomic mass. So, if I were to ask you, how do you find the number of neutrons? The quickest way is to take the atomic mass minus the atomic number. The atomic mass minus the atomic number is the number of neutrons. Sometimes the number of protons and neutrons are equal. Sometimes there are more protons, sometimes there are more neutrons. The number of neutrons can change. So that's why I said put that aside. We'll come back to it in a moment. Hydrogen, by definition, has 1 proton, and it will always have 1 proton. Hydrogen has 0 neutrons. But while the number of protons never changes, the number of neutrons can. See, even though we are calling this atomic mass 1, we're rounding it to the nearest whole number, it's not really a whole number. We see it as 1.0079. You can't have 0.0079 of a neutron. But really what that means is all of the hydrogen anywhere in existence will always have one proton, but most of them will have 0 neutrons. Some of them will have 1 neutron. Some of them will have 2 neutrons. But most of them will have 0. That's where we get this bottom number. We'll come back to neutrons in a little bit. But for right now, we're just going to say, round this to the nearest whole number. Hydrogen, as a general rule, has 0 neutrons. Well, what about electrons? How many electrons does hydrogen have? That's not in this box. Well, it's not in this box directly, but it is indirectly. We see right there, the atomic number is 1, and 1 is the number of protons. And previously we said, in its natural state, the number of electrons is equal to the number of protons. So if we know the number of protons for hydrogen is 1, the number of electrons for hydrogen is 1. The number of protons for beryllium is 4. The number of electrons for beryllium is 4. So we can get a lot of information from these boxes. Now, let's do a little bit of drawing here. There is a proton. We're going to draw hydrogen. So there's a proton. We don't need to draw a neutron. And in its natural state, we know that it has the same number of electrons. So, and we said electrons are found in orbitals. So there's an electron. That, what I just drew, is hydrogen. Atomic symbol H. Let's draw helium. Helium has 2 protons and 2 electrons. For biology, we don't draw the neutrons. We're really not concerned with neutrons that much in biology at all. So all we're going to draw are the protons and the electrons. If we looked at hydrogen, we see we've drawn a proton in the middle and an electron in that shell, that orbital. If we drew helium, we drew the 2 protons and we drew 2 electrons going around it. Now, orbitals can actually hold only a certain number of electrons. That first orbital can only hold a single electron or 2 electrons. If we have more than 2 electrons, we need another orbital. Let's see what that means. Let's draw lithium. Lithium has 3 protons and it has 3 electrons. So let's draw our orbital. It needs 3 electrons, but we can only hold 2 in that first shell. So we have to have another shell. This is lithium. 3 protons, 3 electrons. The second shell, and every shell after that, can hold 8. 8 electrons. So if we drew, let's just jump ahead and draw neon. Neon has 10 electrons. That means that it has 2 in the first shell. We have to draw a second shell, and it is going to have 10 total. 2 in the first shell, 8 in the second shell. If we have 11 or more, then we have to add a third shell. This is neon. But you might be noticing now a bit of a problem. That looks messy. So, how do we actually draw this in biology to make it a whole lot easier? I said on the previous slide, we're going to do a variation of the planetary model. Let's see what that variation actually looks like. We're going to draw some of these same elements using a variation of the planetary model. There are a lot of ways that we could draw this. We get to a point where there's kind of a mess in the nucleus. We have to draw a lot of protons when we start getting up in number. So, instead of drawing a whole bunch of protons, what did we say the definition of hydrogen was? The definition of hydrogen was an element that had 1 proton. So instead of drawing a proton, what if we just draw an H? H is hydrogen. Hydrogen has 1 proton. Drawing an H tells me I'm drawing a proton. And then we draw the orbital. So an H in the middle is a proton in the middle. The orbital around it is the electrons. If I draw helium, I draw He. That tells me there's 2 protons in the middle, and there's my 2 electrons. If I draw, let's jump ahead and go back and do neon again. Instead of drawing 10 protons, I can just draw Ne. That is the exact same thing as saying there's 10 protons there. And all I have to worry about are my 10 electrons. 2 in the first shell, 8 in the second shell. That saves a lot of mess by drawing the number of protons. All I'm drawing is the number of electrons. So let's go back and look at our periodic table. Now we know the atomic symbol, we know the atomic number and what that means, we know the atomic mass and what that tells us. But there's some other things on this table that are important also. First, let's say this is a big table. There's a lot going on there. In biology, we're really only concerned with these purple boxes. We can ignore the yellow boxes. We can ignore the gray boxes. They're still there, but we will not talk about them. They kind of break the rules a little bit. Remember I said the second shell and all the shells after that can hold up to 8? Well, there's really kind of a trick to that. These guys actually can put more than 8 in that second shell. So they break the rules. But that's okay because we'll never talk about them. We are only going to talk about these guys in the purple. And honestly, we're only going to talk about the top 3 rows. Plus a little bit of the 4th row over here with potassium and calcium. Everything else we're just going to kind of ignore. We don't need to talk about it. But those first 3.5 rows on top of the purple, that's what we'll talk a lot about. And that's the ones that I said we're going to talk about so much, you're going to really know what they are if I wrote Na on the board. You're going to know that that's sodium. I'm not going to ask you if that's sodium, but you're going to know. Okay, so now let's look at these numbers going across the top of the periodic table. They're Roman numerals 1 through 8. And those numbers tell us the number of electrons in the outermost shell. Why is that important? Well, the outermost shell is something called the valence shell. And the valence shell is going to be really important in our next lecture, the third lecture of chapter 2. And the valence shell is just the outermost shell. Well, in the case of hydrogen, the valence shell is the only shell. And we can see from that number 1, it only has 1 electron in that valence shell. If we looked at beryllium, atomic number 4, it's in column 2. It has 2 electrons in its valence shell. Boron, atomic number 5, it's in column 3. It has 3 electrons in its valence shell, and on and on and on. The only element that doesn't fit that mold is helium. It's in column 8, but it only has 2 electrons in its valence shell. Sometimes you'll actually even see helium drawn over here in column 2. It kind of doesn't fit neatly in either spot, so you might see it in either location. But everything else in column 8 has 8 electrons in its valence shell. Electrons in the valence shell, we will typically call them valence electrons. That's going to be another really important term in our next lecture. Valence electrons. Okay, so let's build on that. These numbers down the side tell us the number of shells. Going across the top, 1 shell. We drew hydrogen and we drew helium, so we saw those 2 shells. I'm sorry, that 1 shell that had 1 or 2 electrons. This second row has 2 shells. Third row has 3 shells. Fourth row, we're only going to talk about those first 2 we said, has 4 shells. So we know the number of shells and we know the number of electrons in the outermost shell. Those numbers are going to be very, very handy in our next lecture. Now, let's talk briefly about isotopes. Isotopes are weird, and luckily after today, you won't ever deal with them again, unless you are going into radiography. Unfortunately, if you're going into radiography, you're going to deal with isotopes a lot, so that's why I cover these. It's important to know a little bit about isotopes because I know we get a lot of radiography students. So what are isotopes? Isotopes are the same element, but with different number of neutrons. Remember, we said, even though we say hydrogen has 1 neutron, there really are some that have 2. There are some that have 3. So they're all hydrogen. They all have 1 proton. The difference is the number of neutrons. The number of neutrons can change. And if we have an atom of hydrogen that has 1 neutron, an atom of hydrogen that has 2 neutrons, and an atom of hydrogen that has 3 neutrons, they are all isotopes of hydrogen. Isotope is the same element, but with different number of neutrons. So that's what isotopes are. They are used a lot in radiography. So let's build on that. Let's use a thinking cap question. And thinking cap questions, like we said, make great bonus questions on exams. So it's a really good idea to make sure we know what these are. What would be the same among isotopes? And what would be different? See if you can answer that before I give you the response. Well, some of the things that would be the same would be the atomic symbol. All isotopes of hydrogen are atomic symbol H. The number of protons of hydrogen, regardless of the isotope, is the same. The atomic number is the same. The number of electrons is the same. So what would be different? Well, the number of neutrons, that's the definition of an isotope, so the number of neutrons would be different. The atomic mass would be different. The charge would be the same because neutrons have no charge. Changing the number of neutrons doesn't change the charge. So make sure you understand here about neutrons and about isotopes. And that's going to be where we wrap for today. Like I said, in our next lecture, we're going to build on everything that we mentioned today. So make sure that those make sense to you. And I will talk to you in our next lecture.